All right, welcome. Let's practice our partial derivatives. So we're going to work through multivariable calculus homework 2.3, and the first set of problems, it's find dz dx and dz dy. Okay, so number one, z is equal to x to the third plus x squared y squared plus y to the third. Okay. And so to find dz dx, I'm going to treat y as a constant, like 5 or whatever, and then I'm going to take the derivative of anything that has x the normal way. So partial of z with respect to x is going to be 3x squared. All right, the derivative of x squared is 2x, and y squared is a constant, so it's going to be 2 times x to the first times y squared. It's going to stay the same, right? If that was 5, it would be 5x times 2. Okay, so plus 2xy squared, and then y to the third, that's a constant with respect to x, and the derivative of a constant is 0. And the partial derivative of z with respect to y is going to be, okay, the derivative of x to the third with respect to y is going to be 0. And then, okay, I'll take the derivative of y squared, that's 2y, x squared is a constant, so it'll stay there. So 2x squared y. And then the derivative of y to the third with respect to y is going to be 3y squared. Z equals 2xy divided by x squared minus y squared. Does that say? No, that says x to the, no, that's x to the 2. Zoom in on that homework. All right, so both of these partial derivatives are going to involve the quotient rule, and that's kind of annoying that I put these problems that are like super symmetric in x and y. I ask you to find both partial derivatives because you know how this thing is like basically was the same. It's going to be the same this way because you know if you exchange x and y, you're going to end up with the same thing. So partial derivative of z with respect to x is going to be bottom. Derivative of top with respect to x will be 2y. Minus the top times the derivative of the bottom, okay, with respect to x would be 2x minus 0. Divided by the bottom squared. And then the partial derivative of z with respect to y is going to be, all right, bottom times the derivative of the top. The derivative of the top with respect to y is just going to be that 2x. Minus the top times the derivative of the bottom. The derivative of the bottom would be 0 minus 2y with respect to y. And bottom squared. Z equals x squared e to the xy. Right? This one's good because this one's not as symmetric. Okay, it doesn't have x squared y squared e to the xy. So when I take the partial derivative of z with respect to x, this will involve the product rule because I've got the product of two things both in x. So I'm going to take the derivative of x squared while leaving e to the xy the same. Then I'm going to add in, leaving x squared the same, I'm going to take the derivative of e to the xy with respect to x. Well, we know that e to the thing is its own derivative up to maybe times the derivative of the exponent for the chain rule. And the derivative of x times y with respect to x is just going to be y. So, and we can stop there because we don't need the second order partials. I don't need to clean this up or anything. So I'm going to find partial of z with respect to y. And, well, x squared, that's just a constant. So that'll stay there. And e to the xy is its own derivative times the derivative of e of x times y with respect to y. Well, that'll just be that x. And so if we if we were going to need to do anything else with this, we would write this as x cubed e to the x, y. But if all we needed was to write a formula for it, this would be a decent place to stop. Okay, now the fourth one is implicit, so I feel like that might take a little more room than I've got here. Not sure what was going on with that paper, but I can use it. It's had a little bit of something written on it. So I'm going to say number 4. Z squared plus xyz minus x plus y equals 2. Okay, so we're going to take the derivative of this thing implicitly. If we're trying to find dz dx, well, we'll take the derivative of both sides of the equation with respect to x and see what happens. But assuming that z is a function of x. So I'm going to go in, and I'm going to take the derivative of z squared. Well, the derivative of z squared is 2 times z to the first times the derivative of z with respect to x, if we're taking the derivative of both sides with respect to x, which we are. Plus, okay, if we're taking with respect to x, x and z are both like variables, so this will require the product rule. So first I'm going to take the derivative of x and leave yz the same. Then I'm going to add in, leaving x the same, taking the derivative of y times z with respect to x. Well, y is constant with respect to x, but z we are assuming is a function of both x and y, so it's going to have a derivative with respect to x. So it'll be y dz dx minus 1, because the derivative of x with respect to x is 1, plus, okay, the derivative of that is 0. And the derivative of 2 is going to also be 0. Then, just like last year, I'm going to collect all the things that have what I want to one side of the equation and factor it out. 2z plus xy. And that's equal to 1 minus yz. And then I can solve for dz dx. I'll do that here. That's going to be equal to 1 minus yz divided by 2z plus xy. To get the partial derivative with respect to y, I'm going to really go through the same process. That's going to be 2z dz dy. Okay, but now y and z are the things that are variable with respect to y, so it'll be plus, take the derivative of y, leave xz the same. Then leave y the same and take the derivative of xz with respect to y, so it'd be, okay, the derivative of x will be 0 and the derivative of y will be 1 when I'm taking with respect to y. And I'm going to do the exact same thing here. Factor out 2z plus xy. So they'll be the same, but then this will be negative 1 minus xz. And that tells me that the partial derivative of z with respect to y is negative 1 minus xz divided by 2z plus xy. And that's a... All right, 5, 6, and 7 are asking you to find second order derivatives, and, well, that's good. And, you know, with always kind of with the assumption that we're showing that fx is fyx. So, sine y over cosine x. Right, so I'm going to start off with fx. You know, I think for sine y, or wait, we're taking with respect to y, I'm going to leave it like this, but to take the derivative with respect to x, I'm going to write this as sine y times secant x, just so that the thing with the x is in the numerator. Okay, so you could use either of these formulas to start your derivative taking. All right, so let's see. I'm going to start with fx, and then I'll also take fy, and then those can branch off into my second order derivatives. So I'm going to say that fx is the derivative of this product with respect to x. Well, this is just a constant, and the derivative of secant x with respect to x is secant x tangent x. So and then fy is going to be the derivative of sine y with respect to y is cosine y, and then that's a constant, so it's going to stay the same. Okay. So now if I want fxx, that one's going to be annoying. I'm going to start with the mixed partials. Okay, I'm going to take fxy, and that would be taking the derivative of this thing with respect to y. Well, that'll be cosine y, and then these things will stay the same because these are just like numbers that are multiplied by sine y. We know the derivative of 3 sine of t with respect to t is going to be 3 cosine t, so that's why we're still going to have a secant x tangent x there. But if I was to take fyx, should be taking the derivative of this thing with respect to x, this would be a constant, and I would end up with that secant x tangent x just the same. Okay. To get the second partial of f with respect to x both times, I'm going to say fxx is going to be, I'm going to factor out the constant, and then I'm going to take the derivative of secant x tangent x with respect to x. So I'm going to observe the product rule. And I'm going to say derivative of secant is secant x tangent x, but I'm leaving tangent x the same, so I've got 2 powers of tangent. Plus, then I'm going to leave secant the same and take the derivative of tangent x with respect to x, and that's secant squared, so I'll have a total of 3 powers of secant x. Grab this one and take the second partial of y with respect to, of f with respect to y both times. So y is going to be, all right, the derivative of, cosine y is negative sine y, and that's going to stay the same. So negative sine y secant x. Not so bad. Oh, let's scroll that up. Got more room. E to the sine x minus cosine y. Right, so start off with fx is, well, e to the sine x minus cosine y will be its own derivative, and then I take the derivative of respect to x, so that would be cosine x minus 0. Okay. Fy is going to be e to the sine x minus cosine y. You can't see that, but then times the derivative of this with respect to y, which would be 0 minus negative sine y, would be positive sine y. Right, and then fx with respect to y. Oh, yeah, sure enough. So this cosine x will stay the same, and I might actually bring that over here. I take the derivative of e to the sine x minus cosine y with respect to y, and well, I'm just going to get all of this stuff, so I'll have a factor of sine y times still e to the sine x minus cosine y. Whereas if I took the derivative of f with respect to y and took its derivative with respect to x, I'd have, okay, this doesn't depend on x, so it's just a number, so I'll put that out front. And then when I take the derivative of e to the sine x minus cosine y with respect to x, well, I'll get all of this because I already did that. And so I'll have that cosine x here, e to the sine x minus cosine y. And we were expecting those things to be equal because these derivatives are continuous, so that's what you need in order to have equality of mixed partials. I'll drop this thing down here and take this derivative with respect to x. That will require a product rule. So fxx is going to be, I'll take the derivative of cosine x first. If you see that both factors of the product rule are going to contain that e to the sine x minus cosine y, you could wait until the end and just throw your thing around, throw a parenthesis around your thing, and then basically have factored out the e to the sine x minus cosine y. But I don't expect you to see that from the beginning. All right, so fx with respect to x. Okay, so I took the derivative of that and left that the same. Then I'm going to leave cosine x the same and take the derivative of this exponential with respect to x, and that'll just incur another cosine. So plus cosine squared x e to the sine x minus cosine y. Just running out of room kind of here. So fyy is going to be, take the derivative of sine y, leave the exponential the same. Then I'm going to add in, what would happen if I, wait a second, okay, no, then I leave sine y the same and multiply by the derivative of this thing, which is going to incur another power of sine y. So it's all this stuff multiplied by the e to the sine x minus cosine y, because I know that this thing was in both factors when I was doing the product rule, so I was waiting until the end to write it in. Also, because I was running out of room, I don't think I could have written that twice and still had room on the edge of my paper. I don't think it was going to work out. So 7 is x squared over square root of 2y. Okay, what I'm going to do, you see that square root of 2 in the denominator? I'm going to just say, we can always do that. I might even just write this as a power of y in the numerator and then factor out the 1 over the square root of 2, because that's just a number. So I'm going to rewrite this with, this will be something that's easier to take derivatives of, I promise. So the derivative of f with respect to x is going to be, well, just 2x, and everything else will stay the same. So 2 over the square root of 2, that's just the square root of 2. X times y to the negative 1/2. All right, so then I'm going to take the derivative with respect to y, and what's going to happen here? Okay, negative 1/2, so negative 1 over 2 root 2, times, well, x squared is going to stay the same, and y, I'm going to reduce the power by 1, subtract 1 from the power, that would be negative 3/2. And, well, that's good enough for us. Okay. Now, to get fxy, that's going to be taking the derivative of this thing with respect to y. And so that's going to be negative root 2 over 2 times, hold on, I'm taking the derivative of this with respect to y. Yeah, so x stays the same. We're going to reduce the power of y by 1 over here. In taking fyx, we're going to take this derivative with respect to x, and it's really just going to be 2x times all this stuff. So negative 2 over 2 root 2 x y to the negative 3/2. And this is the same because these are the same number, right? We know from, probably from our trig class, that root 2 over 2 is the same as 1 over the square root of 2. You know, run into that number a bunch with 45, 45, 90 triangles. And so these are the same, right? Which is what we were hoping for, because we know that these are going to be continuous because the original function is very continuous. I guess these would be continuous or equal at places where y wasn't 0, though, because the thing's not even defined in the first place where y is equal to 0. So f(x)(x) is going to be, I'm going to take the derivative of this with respect to x. The derivative, that's 1. So it's like all of this stuff is this, you know, like if I had the derivative of 10x is 10. Well, this is all just the 10, and so I'm just going to be left with this. So it would be square root of 2y to the negative half. And then fyy, that's going to be equal to, I'm going to have to multiply by negative 3 halves. So 3 over 4 root 2. Okay, x squared stays the same. Subtract 1 from the power. And there we go. Got ourselves our second order derivatives. All right, and then the last question. Whew, I don't regret putting this one on the homework. Oh, no, this should be easy enough. Pardon me. So, number 8. If f of x and y and z is equal to sine of x e to the y log of z. We're going to take some derivatives. So showing that the mixed partials are equal, f x y z equals f y z x equals f z y x. Okay. So we're going to jump in. Okay. fx is going to be cosine x e to the y log z. fy is going to be equal to sine x e to the y is its own derivative, so it'll be sine x e to the y log z. And fz is going to be, okay, 1 over z times this stuff, so sine x e to the y times 1 over z. And then I'm going to be, the first one, I think from here, I'm just going to go along this one, and the first one it asks for is fxyz. So I'm going to just take fx and take its derivative with respect to y. And then take the derivative of that with respect to z. And so then I'll end up with cosine x e to the y 1 over z. Okay. The next one is fy. So I'm going to take the derivative of that with respect to z. Okay, this is just all constants, and I have 1 over z. And then we want fyzx, so I take the derivative of this with respect to x. All of this is just a constant, so it's cosine x e to the y 1 over z. Okay, 2 for 2 so far. And fzy. Okay, e to the y is its own derivative. And I'm going to take the derivative of all this with respect to x. This is the only thing that depends on x, so it's going to be cosine x e to the y 1 over z, like I'd hoped to show in the first place. All right, I'll probably have another video or two about me doing some partial derivative examples, but that's going to be all for this video.